Okay, let's dive right into today's explainer. We're going to completely demystify complex analysis by transforming what is normally just abstract algebra into this really beautiful visual story. Forget about all those dry, tedious equations you might be used to staring at. Today, we're looking at math through a purely geometric lens, where every single operation is a physical action and every number is literally alive with movement. So, what actually happens when numbers become arrows? It's kind of a simple question, right? But I promise you, it completely flips how we see math. I want you to completely reimagine numbers, not as these static, boring dots stuck on a rigid number line, but as tiny, moving arrows that can stretch, spin, and physically travel across a map. When we make this one little conceptual shift, the entire intimidating world of complex analysis suddenly becomes incredibly intuitive. Section 1. The complex number machine. If we really want to understand complex functions, we've got to imagine two entirely separate worlds. On one side, we have our starting map, which we'll call the z-plane, or the input world, and over on the other side is the w-plane, our output world. A complex function is basically just a physical machine. It eats a specific coordinate point from the z-plane map, processes it, and spits it right out at a brand new location on the w-plane map. Think of it like a set of instructions for teleporting a point from one universe directly into another.
Let's actually look at how this machine behaves in practice. Say we have the function w equals 2z. Well, if you feed the machine an input of 3, it physically moves that point over to 6 on the output map. Simple enough, right? If you input the complex number 1 plus I, it picks it up and drops it at 2 plus 2i. The function is literally just the rule book for how these points get shuttled across from the input world to their final destinations in the output world.
Moving right along to section 2, hunting roots with arrows. Now, you probably remember this golden rule from algebra class. A polynomial of degree n always has exactly n complex roots. But what does that actually mean geometrically? Finding a root simply means finding the exact moment our machine's output, w, lands perfectly on 0 over in the output world. We are basically hunting for that one specific input that completely zeroes out our machine. So, how do we prove this? We get to use this incredibly elegant geometric proof by contradiction. Let's play devil's advocate for a second. Assume w never reaches 0, that there's absolutely no root. Imagine this forbidden, invisible force field around 0 that our output can never, ever enter. Okay, now go back to your input map and draw a tiny circle, walking your input point all the way around it. If you watch the corresponding W arrow in the output map, the strict rules of complex math dictate that it must also turn. And because it's forced to turn and wind all the way around its starting point, it inevitably penetrates that forbidden region we just imagined. Boom, we hit a contradiction. The output is physically forced inside toward 0, which proves for sure that a root absolutely must exist. And that brings us to the complex derivative. Look, this isn't just your standard run-of-the-mill rate of change from Calculus 101. No, in this world, it's a tiny arrow transformer. When you nudge an input point just a tiny bit, the derivative steps in and tells the output point exactly how much to physically stretch its length and exactly how much to rotate its angle. It's literally the engine of the entire transformation. Okay, section 3, counting roots by turning. This is where things get truly magical. We can count these roots without doing any hard algebra whatsoever. Think about walking your input arrow in this massive sweeping loop. If there happens to be a root trapped completely inside that path you walked, the angle of your output arrow is going to turn all the way around, increasing by a full, complete circle. But if you just walk past a root so it stays safely outside your path, your output arrow might wiggle back and forth a little bit, but it will inevitably snap back to its exact starting angle. The total net change is just 0. And this leads us to something, well, absolutely astonishing. Every single root trapped inside our little geometric loop, it contributes exactly one full 2 pi rotation to our total angle count. If your output arrow spins completely around 3 times, congratulations, you just found 3 roots trapped inside your path. No equations, no heavy lifting, you literally just sat back and watched the arrows dance. Actually, before we move on, I should probably mention that sometimes our complex machine spits out multiple valid answers for a single input. Take the square root of 4, for example. It could be 2, sure, but it could also be -2. When this happens in complex analysis, it creates entirely different branches of mathematical reality. You literally have to make a choice about which branch of reality your machine is going to operate in. Section 4. The Cauchy-Riemann dance. So what's actually going on underneath the hood here? Well, a complex function is really just two ordinary, everyday real number functions strapped together. One function handles all the real horizontal coordinates, which we call u, and the other takes care of the imaginary vertical coordinates, which we call v. But here's the catch. They can't just run off and do whatever they want. They have to work together simultaneously to create a valid complex function. And that brings us directly to the Cauchy-Riemann equations. Now, don't panic about the algebra here. Just think of this as a super strict mathematical compatibility rule. It is the necessary choreography that forces that u function and that v function to dance together in perfect harmony. If they nail the choreography, the function is properly differentiable from all directions. If they step on each other's toes even a little bit, the whole complex magic trick completely breaks down. Which leads us to our grand finale, Section 5, Shape-Shifting Conformal Maps. When our functions actually follow that perfect choreography we just talked about, they unlock this absolute superpower known as conformal transformation. This is basically an angle-preserving magic trick. If you draw a tiny shape on your input map and shove it through the machine, it will arrive on the output map scaled and rotated, sure, but it will never, ever warp or distort. A tiny circle remains a perfectly round tiny circle. A tiny triangle keeps its exact same angles. The overall grid of our universe might bend, but the tiny, localized shapes, they are flawlessly preserved. Let's put this into action. Think about the mechanics of a specific conformal map, like the squaring machine, w equals e squared. How do you physically square a complex number geometrically? It's literally just a two-step process. Step 1, you physically square its distance from the center point. Step 2, you take its angle and you just double it. That's it. Square the length, double the rotation. And when you apply that rule, just squaring the distance and doubling the angles to a whole collection of points, the geometry you get is just mesmerizing. Because the angles are all doubling, a rigid, straight line magically folds right into a sweeping, curved parabola. And if you drop a semicircle into the machine, doubling all of its angles wraps it all the way around until it expands into a full, perfectly closed circle. The shapes of the universe are literally folding around themselves. But here's the real mind-bending part about this squaring machine. It's a 2-to-1 deal. If you put in a 2, the output is 4. But if you put in a -2, the output is also 4. Because squaring just inherently removes negative signs, two completely different points on your input map land on the exact same location on the output map. So the machine is quite literally folding the entire input map completely over onto itself, almost like a piece of paper. Just take a step back and look at the crazy journey we've taken in this explainer today. I mean, we literally started with a simple, static, complex number. We imagined it coming to life as a moving arrow. We fed it into a function machine just to watch it transform. We used a derivative to dictate exactly how to scale and rotate it. And finally, we zoomed all the way out to witness the grand, shape-shifting masterpiece that is conformal mapping. I actually want to highlight a quote directly from our source material because it really hits the nail on the head for everything we've talked about. Squaring a complex number means square its distance from the origin and double its angle. That geometric idea is the bridge to the much deeper subject of complex analysis. By deeply visualizing this one single geometric action, you've essentially unlocked the doorway to the entire beautiful field of complex math. So I'm going to leave you with this. We just looked at what happens when you simply square a number. But if squaring a complex number is powerful enough to bend straight lines into sweeping parabolas and literally fold a mathematical universe in half, what infinite, mind-bending shapes are waiting to be unfolded when we start exploring the countless other functions out there? Keep exploring, keep visualizing, and I'll see you in the next explainer.